see in the figure, there is a disc and it's rotating with angular speed omega. The lower end of the rod is rotating with disc, while the upper end is just static in air. It's not touching anything, it is just at its position only. And we have to find the omega for this to happen. The length of rod is given, this distance is given as r, this height is given as h. Okay. So consider a small segment in the rod. So just take a small segment. Let this small segment be at a distance x and its length be dx. And at this instant, velocity of the segment is inwards, because the omega is like this. So the rod at this instant is moving inward. With respect to point P, the angular momentum is r cross mv. So for this particle, r vector is this x vector and mv is inward. So if you find the direction of cross product using right hand rule, x cross mv, so it will be in this direction. And its value will be mass. Lambda is suppose mass per unit length. So lambda dx, this is mass into velocity. So velocity will be, suppose this distance is y. So this element is moving along a circle of radius y. So its velocity will be y into omega. So m v into x. So this is the angular momentum about point P and its direction is as shown. And since there are many elements in this rod, we have to integrate this to find the total angular momentum. So this is total angular momentum of the rod. So lambda, omega, these are the constant quantities. Integration x, y, dx. And suppose this angle is theta, so y will be x sine theta. And sine theta is a constant that can be taken out of the integral sign. So it will be x square dx. And the limit of x will be from 0 to the total length of rod. So if we solve this, lambda into L will make mass m omega sine theta L square by 3. So this is the result we get for angular momentum of the rod. Now as the rod rotates, this angular momentum vector will also rotate. So it will rotate like this with angular speed omega, and the rate with which angular momentum changes, that is d by dt of angular momentum, that is equal to torque. So for that I am just resolving this angular momentum into two components, Lx and Ly. As angular momentum vector rotates, Ly vector does not change, only Lx vector rotates, and therefore d by dt of L vector is Lx into omega. As we have seen in earlier video, if you haven't seen my earlier video, please do that, because in that I have derived this result, Lx into omega. So this is equal to torque. So this much of torque should act on the rod. Okay. And angular momentum we have found as this. So Lx is, if this angle is theta, see, we took this angle as theta, this would be 90 minus theta, so this will again be theta. So Lx is L cos theta into omega. So this is torque, and we put the value of L. So this is the value of L, and omega cos theta we have to multiply. So this much of torque should act on the rod. Now see the forces acting on the rod. There is no force at this free end, because it is simply free. Apart from that, the weight of rod will act at its center. there is a normal from disk, and there is a friction from disk. So these are the forces acting on the rod. The center of rod, that is center mass, it rotates along a circle of radius r by 2. So if we write equation for center mass, so it's a particle of mass m, that is mass of rod. All forces acting on the rod will be transferred to center mass. So N, F and mg, all forces will get transferred to it. And so this is force diagram, and its acceleration is towards center, omega square into radius is r by 2. So now write Newton's laws. So N and mg must cancel out because there is no motion in vertical direction. And the friction should be equal to mass into acceleration. So friction is towards the center and acceleration towards center is omega square r by 2. So these are the values of N and F. So now again N, so we have got the value of N as mg, we have got the value of friction, which is m omega square r by 2 and mg. So these are the forces acting on the rod. Now the torque we obtained earlier, so this was the torque that must act on the rod, and the direction of this torque, since this Lx is moving inward, so this tip it's moving inward, so the rate of change of Lx is inward, so this torque is inward. So we have to find inward torque to equate with this quantity. So what is inward torque? Inward means if you put your thumb, right hand thumb in inward direction, so your fingers will rotate like this. We have to find torque in this direction. So with respect to P or about P, mg will rotate along this direction. So its torque will have mg into perpendicular distance, so that is r by 2. Friction will also have a tendency to rotate in this direction. So plus friction into this perpendicular distance, which is h, and N will have a tendency, opposite tendency. So minus N into perpendicular distance from P. So this is R. So this is net torque, and this torque should be equal to the torque required. So I'm just putting the values of friction and N we just obtained. So friction was m omega square r by 2, N was mg. So this much of torque we have obtained, and this torque should be equal to the torque required. So it was this much. So I am equating these two. This will give the value of omega, L sin theta into L cos theta. So we had this length as L, this angle we took as theta. So L cos theta is h and L sin theta is r. So here this term I am changing. Now finally we have to solve this. So this is the result we obtain.